Overall, I was not unhappy with the exam. Some summary data for you. Average, standard deviation, a median, and a maximum. You should be able to see more of your performance within the course, within the exam results on Canvas directly. There's a little bit of statistics it will provide you with. Additionally, you can look at your gradebook grades, and as far as I can tell at this point, those are accurate. So if you have questions about your grades or what you can do to improve from here, please come talk to me. The key was posted as soon as the grades were. If you have questions about the exam questions specifically, please start by taking a look at the exam key. Then you'll know what I was after. And if you're still like, where did we learn this? Then come talk to me. All right? Meanwhile, I want to continue what we were working with our contingency tables and our probability ideas. What was our definition for independent events? I know it was Wednesday, so it's, sorry, Monday. It's been a while since we talked about this, but let's see if we can nail that back down. Right, if having an independent event means that your regular probability is equivalent to your conditional probability. In other words, gaining extra information really doesn't change the probability of something occurring. So let's check. Remember, all of the information we are working with came from the contingency table that's in example. I wrote down the example number, 5.3 on page 170. So this table is on page 170. Let's ask if engagement, high engagement, is independent of being a member of the executive MBA group. Are these, if you know a student is part of the executive group, are they more likely or less likely to be highly engaged? Or are those independent ideas? So if I want to answer this question, I need to look at two probabilities. I need to look at the chance that I have a student who is in that high engagement class. And I need to be able to tell what's the chance that they're in that high engagement class, given that they are a member of the executive MBA group. So with our table, what do you have for the probability of someone being in the high engagement group? Say again? That's how many people there are in that group out of how many total? Aha. So the chance of being in the high engagement group, 27 out of 360. If you want, you could give me a decimal. I'd be perfectly fine with that. But now, what's a chance that someone, if you know they are in the executive group, is in the high engagement class. How do we do the conditional probability calculation within there? And how'd you get that? Aha. Since I'm looking at the conditional, I ignore everything in the table except my given. I am given that they are a member of the executive MBA group. So I look at this row only. Out of the 37, 15 are in the high. Those are not the same number, are they? I can say with complete certainty, executive membership in the executive MBA program is not independent of high engagement. This number is higher than this number. There's no correlation required here, but it is more likely, given someone is an executive MBA person, to know that they will be highly engaged rather than just knowing somebody's in high engagement overall. By the way, you could take this entire table and rewrite it in terms of percentages. Divide everything by 360. You'd get different numbers, but all of your calculations would work the same. Instead of using the absolute frequency numbers, you're using the relative frequency numbers from a histogram. So having a contingency table allows an easier calculation of conditional probability, and thus an easier determination of whether or not two events are independent. Questions? Me? How many of you have heard of or used tree diagrams before? Or decision trees? Oh, goody, something we're doing that's brand new to everybody. So, let's look at some funds for a contingency table. We have 3 different kinds of expense ratios and 2 different kinds of funds. So here's my contingency table that starts. But instead of continuing to work off the table, I want to work off of this new idea of a tree diagram. So I need to decide how we're going to group these first. Do you want to group by type of fund first or by expense ratio first? Your call. We're going to go by row first or by column first? Your choice. Column. If I go by column first, then I start by looking at dividing each number by its column total. And what I'm doing is I'm building conditional probabilities. So remember, what these are going to be divided by 21. And these are going to be divided by 23. Now, what do these numbers represent? If you're in that first column, these numbers represent the probability of low or medium or high given that you are a bond fund. These numbers represent the probability of low, medium, or high given that you are a stock fund. But the question here is, what's the chance that if I pick a fund at random, it's a bond fund? Pardon? Exactly. And the chance that if I pick a fund at random that it's a stock fund is 23 out of 44. Those were the column totals, weren't they? So, the joint probability. Here's what I'm going to do. I'm going to make a tree because you have a choice. You choose which column you're in, and then you choose which row you're in. And the only reason I'm doing it column first is because you said column, Matthew. So, my first choice is bond versus stock. My second choice is whether my expense ratio is low, medium, or high. But now here's the best part. I can take the probabilities that Carter came up with for the choice that I make a bond fund, and I can write it right here. The choice that I make a stock fund, if I pick one at random, notice that column sums to 1. On each of the branches, now I see the tree diagram idea, up here, write this corresponding conditional probabilities. Probability of low, given that you're a bond fund. Probability of medium, given that you're a bond fund. I can put all of those probabilities right here, and I can just draw them directly from this table. Again, notice these 3 items. Their total is 1. Fill in the numbers on the bottom branch, set, and you'll notice that their total is also 1. The definition of joint probability, probability of A and B, came out of our conditional probability formula. What's the formula for the probability of A and B? Again, we wrote it down Monday, a week ago. Well, it's the one that ended up from our conditional probability form. But there's one for P, A, and B that involve my conditional probability.
A/B times P of B.
The conditional probability is something given bond. Is right there. It's on the branch, 21 over 44. So if I want to know what is the chance of bond and low, let me write it the other way around, low and bond, well, then that's the chance of low given bond times the chance of bond. Wait a minute. Those are the numbers on the branches, aren't they? I can multiply along the branches to figure out my joint probabilities. I need 6 numbers from you all. At the end of each branch, I want you to write the probability of the total joint across those branches. So at the end of this branch, I want you to put the probability of L and B. On this one, you'd be putting the probability of M and B. All right, let's just label them before we actually write down the numbers. You think about the branch is your decision. What's the chance I got a stock? What's the chance from that I got high? Well, that's stock and high. Now I can simply multiply these numbers across to get a total for each one. What do we get here? In that very top row as our joint probability. You're welcome to give me a decimal. You can also give me a fraction. I don't care. I'm pretty sure you made a round off somewhere. So that's going to actually turn out to exactly be 0.25. Because if I take these two numbers, 11 over 21 and 21 over 44, won't the 21s cancel? When I multiply, I'll get 11 over 44, which is exactly 0.25. Because one of the bottoms is 21, that's a big, ugly decimal. If you chop off the decimal somewhere, you're going to get a little bit of a round off error. That's okay. But what that does mean is that our total might be slightly different. Keep going. What's chance here? Exactly. And on we go. And if you total up all 6 of those numbers, you get Now, I said it was an arbitrary choice that Matthew picked. We're going to go by columns first. What if we went by row first? We'd have a different tree, but the decisions and the resulting probabilities would be identical. So now I have a new diagram. And as a result, I need to go back to my table. And instead of dividing by the column totals, I need to divide by the row totals. So, in L, the row total was 14, right? So there were 14 of 44 that went there. And medium, it was 16. And in high, it was 14. But now if I go back and I look at the column, the table again, which I will pull down just for a moment so we have it with this, I divide by the 14. So this is 11 over 14 here and 3 over 14 here. Those are my conditionals. And 7 over 16 and 9 out of 16. 3 out of 14 and 11 out of 14. And if you carry out the same multiplications we did, you will get exactly the same fractions. Because this calculation right here, probability L and B, is the same as the probability of B and L. Doesn't matter which one you do first. And that gives me that same 1/4, 0.25, 0.248 if I did the round off. You'll get a different round off here because 11 over 14 will give you a different fraction, and where you round that might change it again. I'm a geek. I like working in fractions. You don't have to. Questions? All of this bases itself on using a contingency table. So I need that contingency table in there. But now I can ask the same questions. What's independent? What isn't? Are low and stock independent of one another? What's the chance of low? Low fees. Chance of low fees. Bingo. What's the chance of stock given low fees? Which is definitely a different number, isn't it? They're not independent. I have all the information sitting here, just like it was sitting in the contingency table, to tell me about whether or not my two ideas are related. And I will freely admit conditional probability is a pain in the ass. But this is a better way to get at it, I think. You can have a decision tree for as many options as you want. Whereas in our table, we had trouble. If we had 3 different things that we wanted to look at relating, I would just add another layer of branches. I could do that. But then the conditionals get really complicated. And then we have to slice our table up. How do you make a 3-variable table? Well, that's several different tables all layered together, isn't it? With different values for that 3rd variable. That's much more complicated to try and visualize. But as a tree, it would just be another layer of decisions. All of our conditional probability ideas descend from one result. A guy by the name of Bayes wrote a result called Bayes' theorem. And this is a kind of different way to approach conditional probabilities based on the way our contingency tables work. There are two versions of it, but they basically both boil down to reimagining this formula. That's our definition for conditional probability. That's why I asked you for it earlier. I'm going to change the way we write this formula just a little. All right, wait a minute. What did I just do? What I did was I reversed conditional probability. The chance of stock given low in our previous example. You just told me what that was. What was the chance of stock given low? Somebody say it again. I heard it. 9 out of 16? 9 out of 14. The chance of stock given low is 3 out of 14. What's the chance of low given stock? That's not up there, is it? It's on our other version of the table. The chance of low given stock, 3 out of 23. So if you'd done the work one way and you wanted to get it the other way, you don't always have to build a new tree. You could reverse the condition, and Bayes allows us to do that. Okay. What if this is not a number I know on its own? Well, it turns out there's another version of this result. That changes the bottom where I don't have to know the probability of A all on its own. Wait a minute. Wait just a minute. The hell is B prime? Say again? The complement. That's not B. So notice that I can generate the probability of A by looking at the part of A that happens when B happens and the part of A that happens when not B happens. The denominator, by its very definition here, must be larger because it's everything that's on top plus more stuff. How does this work? Well, this either works from a contingency table or from a tree diagram, and it allows me to walk through and figure out all the pieces I want to know. Bayes' theorem shows up in testing. Okay, in the past 12 months, how many of you have taken a COVID test at all in the last 12 months? None of you. Oh, I got a couple hands. How many of you have taken a drug test in the last 12 months? I had a summer job that made me take a drug test, right? How do you know whether or not it's accurate? My wife used to work in Squirrel Hill at a bagel store. One morning, she has two gentlemen in black suits, black sunglasses, and earpieces come in going, "Do you know this person?" With a picture. MIB, here to talk to my wife. A person had applied to the FBI office in downtown Pittsburgh and had tested positive for opiates. Why did they go to my wife at the bagel store? Louder. Poppy seed bagels show up as positive opium tests. They think you do heroin if you eat a lot of poppy seed bagels. So they wanted proof from the bagel store that you see this guy every morning. He comes in, buys coffee and a poppy seed bagel. That's what he told us. Do you know this guy? Yes. Yes, I see him every morning. But if you randomly are drug tested or you take a COVID test, let's make an assumption about our errors. Let's think this test is not 100% perfectly accurate all the time. So let's suppose we have a drug test and 5% of the time it gives a false positive. What does that mean? Sorry? Oh, but what is that? What does the false positive idea mean? Well, but that's what I'm asking. What's a false positive? Right. It's a positive result. This says I do drugs and I don't. And same test has a 10% false negative rate. Now, I'm about to make a dramatic assumption about the population of people who are applying for this job and have to do the test. I'm going to assume for the moment that actual drug usage is about 4%. You show up, out of this population, you have a positive drug test. Chance the person who has a positive drug test actually uses drugs. Now, this does not have to be a test for opioids like I was describing with the poppy seed bagel kit. This could be a test for performance enhancers. And the NCAA tests all of our athletes on a random basis. So it is very possible that some of you will be taking a drug test this year due to your participation in an NCAA sanctioned sport. All right, wait a second. A human being walks in and takes the drug test, there are two choices. Either they are a drug user or they are not. For the drugs that we are detecting, we're going to make that our first branch in our decision tree. Either a person does use drugs or they do not. You should be able to put numbers on both of those branches. What number goes on this branch up here? Based on the information we have. The top one? I want to use percentages, so I'll make it 0.04, right? 4 out of 100. And the 96 goes where? On the bottom branch. If drug use is actually 4%, then 96% of the people who walk in to take this test are clean. Now, unfortunately, the information I want has just rolled off the top of the screen. This person takes a drug test. It's either going to be positive or negative. I should be able to put numbers on those branches. Unfortunately, we know. If this person uses drugs, the chance that they get a negative test is a false negative, right? So what's the chance of a false negative? 10%. So down here I get 0.10. What goes on the top branch? Is it 50-50? 0.05? Wait a minute. If somebody who uses drugs doesn't have a negative test, then they have a positive test. That should be, because this box should add up to 1. That's going to be 0.9. What about down here? Somebody who does not use drugs takes this test. What is the chance that it shows a positive result? Because that would be a false positive. That's 0.05. Which means down here, 0.95. So wait a minute. I now have a bunch of interesting information here. Let's label these numbers with what probabilities they represent. That 0.04 on the top left, that 0.04 is the chance that a randomly selected person actually used drugs. So that is probability of D. What's this 96? So it's the chance that someone was not a member of the drug using group. The complement. The 4 numbers on the middle branches, those are conditional probabilities. Because it depends on which branch we're on as to which number we get, right? So this 0.9 up here at the top, what conditional probability is that? Say again? That's not a, that's, you just use the word and. And is a joint given what? Given that they do drugs, they got a positive test. So this is the chance of positive given drugs. Because we're on the drug branch already. Now we're trying to decide between positive and negative. So the 0.1, what does that label? The chance of a negative result given that they are a member of the drug-doing population. On we go. There are 2 more things for us to label. The 0.05. Positive test given that they are not in the drug population. And this 0.95 is the chance of A negative test given that they are part of the non-drug using population. What did the question ask for? Oh, wait a second. Be careful the way you say that, Matthew, because this is where it becomes a matter of how we say it. I want to know the chance that someone does drugs, given that I see a positive test, right? So I want to know, what is the chance that someone does drugs given a positive test? Notice that that probability is nowhere to be found over there directly. And if I wanted to use Bayes' theorem, I would either need the chance of a positive test alone, which I don't have anywhere here, do I? Or I would need to try and reverse these sorts of behaviors, right? I want to turn this one around. That's this. I want to reverse what's been given to me. So I'm going to use this version of Bayes' theorem. Bayes' theorem version 2. The probability of drugs given positive is equal to the probability of positive given drugs over probability of positive given drugs, that should be a D, times the probability of drugs, plus the probability of positive given no drugs, times the probability of no drugs. See how the complement shows up? But all of these numbers are in my tree. So please fill in all the appropriate numbers in all the appropriate spots. I have a copy error. What's my copy error? You're looking at me like I did. What is my mistake? The first one should be
with the one instead of
which first one?
on the bottom.
Given D. That should be the same as this. So that is correct. What's missing is this. P of D needs to be up there as well. That was my mistake. Remember, this first piece on the bottom is the same as the top. When I looked over and I only saw one thing on top, I realized I effed up. Got to copy the formula down or you will screw up everything else. I apologize. My mistake. I wrote it there, right? But now I can put in all the right numbers because these top numbers are known. Positive given drugs, that was the 0.9. Chance of drugs was 0.04. What was the chance of positive given no drugs? That is correct. And the chance of no drugs Time to do some arithmetic. Grab your calculators. Let's start multiplying. On the top, I get 0.036. What do I get on the bottom? I get 0.036 plus something else. Which gives me 0.036 over 0.084. When you actually divide, what do you get? If you show up with a positive drug test, I can only say that there's a 43% chance you're actually a drug user, based on a test with a 5% false positive and a 10% false negative. People, I don't care what you're testing for. You want your test to be sufficiently accurate. I have 4 more minutes. Please stop hacking. I promise I will let you out on time. No matter what you're testing for, I don't care if you still have a COVID test somewhere in your house, open up the instruction sheet. Find out what the false positive rate is. Find out what the false negative rate is. And it doesn't have to be a test like this. We could be looking at our stock option and bond funds from just a moment ago with that decision tree, right? But what if I wanted to know what the chance of a stock fund was given it's low or it's medium? I have more than 2 options there, don't I? Here I had drug user, non-drug user. It was just a one or the other. If I have more than 2 options available to me, I may run into the situation where I need to have a larger denominator. There is a longer version of Bayes' theorem that works for more options. Down here on page 180. So instead of just having 2, we had B and not B. Now we have B1, B2, B3 up to B whatever, N. Then I can look at one of them, BI, but then down here I need to look at all the rest of them as well. I need to look at my different, notice it says right here, these are collectively exhaustive and mutually exclusive. So there's no overlap between B1 and B2 or B1 and B3 or B2 and B3, no matter how many options you have. Well, that made sense. It was either a low fee, a medium fee, or a high fee. You couldn't be 2 of those at the same time, could you? So this version is more general and therefore can be used in more situations like we have down here with lawsuits being filed at hospitals. I don't know if you're going to go into hospital management. It's a hell of a track. There's a lot of money in that right now. Healthcare administration is not small. But this is the sort of place I would use that behavior. How likely is somebody to file a lawsuit depending on which hospital they went to? Now, how likely am I to be sued, period? Again, it starts with a contingency table or a tree diagram, which in this case is easier. That example covers a little more than 2 pages, page 180 to 182. I hardly recommend you read it. As crazy as it sounds, we are almost done with this idea of theoretical probability. But we have to be able to count large sample spaces. So on Wednesday, I'll talk about the counting rules, and then we'll move on to what our probabilistic behavior does from here. And how do we do statistics with this information? If you came in late and I still have your exam, please come get it. That's how I'm taking attendance today. So if I still have your exam at the end of class, you're not here.